Hello, everybody. Hello, colleagues. Today I would like to present the results of experimental work which was carried out by the Institute of Macromolecular Chemistry of Kiev in collaboration with Sabatier University of Toulouse, France. Today we'll talk about hybrid polyion complexes and their possible application in catalytic processes. So, how bimetallic and multinuclear catalytic systems have demonstrated superior performance and key transformations such as oxygen reduction, hydrogen evolution, and CO2 reduction, where electron and proton transfer mechanisms are essential. Understanding and optimizing these interactions leading to improved reactant activation, electron transfer, and intermediate stabilization provide valuable insights for the design of highly efficient catalytic systems. In this context, the use of copper-based hybrid polyion complexes may be of particular interest. Probably I will ask you to change the pictures, please. Yeah. Let me remind that hybrid polyion complexes called HPICs are formed when water-soluble block of polymers comprising ionizable complexing block and neutral block interact with polyvalent metal cations in water solution. Such complex formation resulted in stable nano-objects with core shell structure consisting of a core rich in complex ions and hydrated shell formed by the neutral blocks. Next, please. There was reported the formation of stable hybrid colloidal suspensions when mixing multivalent metal cations with double hydrophilic block of polymers containing polycarboxylic acid block or polyphosphonic acid block. Such systems have been employed as highly efficient contrast agent or templates for the preparation of metal hydroxide, oxide, or sulfide nanoparticles. HPICs loaded with copper or iron have been also been successfully used as homogeneous catalysts for the degradation of naphthol blue black via a photophantom-like process. Next, please. In the present study, we investigate colloidal structures based on hybrid polyion complexes formed by the complexation of copper ions with double hydrophilic block of polymer comprising neutral polyvinyl pyrrolidone block. You can see this scheme of complex formation and the ionizable polyvinylamine block for the PVP, PVA. And we evaluate the ability of mentioned HPICs to promote synergetic effect in O2 activation reactions. It's necessary to say that polyvinylamine is a water-soluble polymer with high content of primary amine groups, which is easily complex with metal ions. So the use of polyvinylamine instead of more commonly used polyacrylic acid is expected to enhance interactions with copper ions. PVP-PVA block copolymer was obtained using rough techniques. You can see a scheme in the picture. In the first step, PVP macro chain transfer agent, PVP-ST, was prepared. And then, unfortunately, I don't know if it's, can you see if it's seen? Is it seen if I show? Hello?
We can see only your slide. Your mouse
only slide, but I cannot point the. Okay.
Yes, because it's our screen share. If I know where to point, I can do it, but I don't know, and we will waste too much time if we do it.
Okay. Okay. On the next step, on the next step, PVP-ST was used as a macro agent for the polymerization of vinylformamide, and then polyvinylformamide block was fully hydrolyzed under basic conditions, forming the polyvinylamine block. Next, please. To understand the To understand the peculiarities of ash peaks formation, increasing amount of copper sulfate was added to the constant amount of block copolymer so that the molar ratio between copper ions and amine groups of polyvinylamine block changed from 0 to 1 to 0.2. Obtained compositions were examined by UV spectroscopy and conductometry. As the formation of the complex was confirmed by the presence of a band with lambda maximum 594 nanometers, figure 1a. Above a given concentration of copper sulfate, a new band was observed at about 800 nanometers, which means the appearance of free copper ions. Then absorbance was plotted as a function of ratio between copper and amine groups to determine the stoichiometry of the complex formed. This is figure 1b, black line. A change in the slope was observed at ratio 1 to 4. This result was confirmed by the conductivity, figure 1b, blue lines. While the conductance of pure copper sulfate solution increased linearly with concentration, the conductivity of the polymer containing solution remains constant up to ratio 0.2 and then increased with a slope comparable to that of the copper sulfate solution alone. Hence, absorbance and conductivity measurements highlighted the formation of complex, which is complete complexation when the ratio between copper and amine groups of polyvinylamine blocks is close to 0.2. It should be noted that the same result was previously described in the literature for the complexes between polyvinylamine homopolymer and copper. Next picture, please. To obtain the kinetics of copper loading at molar ratio 1 to 4 between copper ions and polymer, we followed the evolution of maximum absorbance as function of time directly after the addition of copper sulfate to polymer solution. Obtained kinetic graph, presented in figure 2a, shows very fast complex formation, which is completed within 5 seconds. The ash peaks formation was also proved by dynamic light scattering, figure 2b. In the absence of copper ions, polymer form polydisperse and large aggregates appear due to ash peaks formation. The diameter of these aggregates at the ratio 1 to 4 is about 20 nanometers. Next, please. Transmission electronic microscopy shows small, high contrasted domains with an average diameter of about 4 nanometers, figure 3a. These domains presumably arise from the copper-rich complex core, and zeta potential, figure 3b, was measured at 2.9 milliwatt for copper ash peaks, whereas its value for a pure polymer solution is equal to 3 milliwatt. It indicates a slightly positive surface charge. Therefore, the less stem and zeta potential data strongly support the formation of ash peaks as follows. Upon addition of copper ions to the block of polymer, a rapid complexation with PVA block occurs when a ratio between copper and amine groups more than 0.12. This interaction led to the formation of ash peaks nano-objects with a polyvinylamine core cross-linked by copper ions surrounded by a neutral PVP shell. Next, please. It was interesting to evaluate the colloidal stability of ash peaks. For this purpose, copper ash peaks samples were prepared in the presence of different amount of sodium, 1 molar sodium chloride. As can be seen from the UV spectra, figure 4a, sodium chloride doesn't lead to the destruction of the complex, and ash peaks remain stable even at very large excess of sodium chloride.
Sorry for interruption. One moment.
Yeah.
Moment, we will share the screen properly because it was one stop disconnection. I will tell you when we will ready. Okay, now you can continue. Sorry.
So I will describe the slide, the picture number 8 again. Yeah.
Yes.
from the very beginning. It was interesting to evaluate the colloidal stability of ash peaks. And for this purpose, copper ash peak samples were prepared in the presence of a different amount of 1 molar sodium chloride. As it can be seen from figure 4A, UV spectra doesn't show any changes. So sodium chloride doesn't lead to the destruction of complex and ash peaks remain stable even at very large excess of sodium chloride. It should be added that DLS measurements also do not reveal any aggregation or decomplexation phenomena. So we can say that stability of ash peaks isn't governed by electrostatic forces, but rather by steric stabilization provided by hydrated neutral corona. Additional experiments were conducted to evaluate ash peaks' colloidal stability over a pH range from 9 to 1, figure 4B. With pH lowering, we observed a decrease in copper binding band caused by decomplexation. From pH 9 to 6, the absorbance of ash peak solution remain roughly constant, suggesting the complexes remain intact. Lowering the pH down to 4 led to a significant decrease of measured absorbance. Below pH 4, the absorbances sharply decrease. And UV visible spectra show only a weak band around 800 nanometers corresponding to free hydrated copper ions. These results confirm that the interaction between copper ions and amine groups are driving forces behind ash peaks assembly. Next, please. At the next stage of our experiments, we evaluated whether the obtained ash peaks could be applied in catalytic processes. For this purpose, we selected ascorbic acid as model substrate and studied its oxidation by atmospheric oxygen in the presence of copper ash peaks. The oxidation was carried out with copper to substrate ratio of 1 to 5 in water under saturated O2 at 50 degree. As controls, the oxidation of ascorbic acid without catalyst and in the presence of copper sulfate were also examined. The oxidation of ascorbic acid was followed by the decrease in its absorption at 260 nanometers. As we can see from the picture, in the absence of copper catalyst, the conversion of ascorbic acid is below 5% after 20 minutes. The oxidation was faster in the presence of copper sulfate, with a conversion equal to 40%, and the complexation of copper ions within the ash peaks enabled to reach a conversion to 61% after 20 minutes for a ratio 0.2. Therefore, a copper ash peak seems to positively influence the ascorbic acid oxidation process. This naturally leads to ask, what is responsible for this effect? Is it the special colloidal structure of ash peaks, or it is simply due to copper complexation? Next, please. In order to answer this question, a series of experiments were conducted at constant concentration of ascorbic acid and copper, but different concentration of polymer. Another thing, in this experiment, we keep a constant concentration of ascorbic acid and copper ions, but we change ratio between copper and amine groups inside of ash peaks, inside of copper polymer mixture. Corresponding rate constants were estimated as and plotted as function of amine concentration, figure 7. And it turned out that in the absence of polymer, the reaction proceeds like in the presence of copper sulfate. When polymer is added in insufficient amount to fully complex all available copper ions, its ratio more than 0.25. A slight decrease in the rate constant is observed compared to free copper sulfate. When the polymer amount was enough to complex most of the copper ions present and it induced the ash peaks formation, this is the ratio between 0.12 and 0.25. A significant increase in the rate constant is observed. And as we can see, the most effective catalytic condition shows ratio 0.14. The presence of an excess of polymer at ratio less than 0.12 leads to complete copper complexation, but prevents the formation of colloidal complexes. In these conditions, the resulting constant values are lower than those of free copper sulfate. Next, please. Another factor that may influence the catalytic effect is the distance between copper ions within the ash peaks and the existence of cooperative interactions between copper ions. To verify this assumption, an experiment was carried out using the most catalytically efficient condition at ratio 0.14. To modulate the average distance between copper ions under these conditions, some of them were partially replaced with cobalt ions within the ash peak structure. It's necessary to say that, like copper, cobalt can complex with amine functions, but it doesn't catalyze ascorbic acid oxidation. So cobalt was a very suitable object to modulate different distance of copper ions. As we can see from figure 8a, the best efficiency is observed for the ash peaks containing 100 copper ions. In the presence of cobalt ions, catalytic activity is decreased. As it's shown in figure 8c, in general, activity in copper-cobalt ash peak systems is systematically lower than that in copper ash peak system with the same copper concentration. The nonlinear variation observed in copper-cobalt ash peak systems confirm the effect of the distance between two metal ions. Any modification of this distance rapidly induces a sharp decline in catalytic activity. And next picture, please, with conclusion. So, a series of colloidal structures based on hybrid polyion complexes, ash peaks formed by the complexation of copper ions or copper-cobalt mixtures with a block of polymer containing vanillamine were designed. Obtained colloids have well-defined dimensions and demonstrate a catalytic activity in reaction of ascorbic acid oxidation by air oxygen. The main factors influencing the catalytic activity of ash peaks are copper content and the average distance between copper ions. Modularity of ash peaks enable to integrate different metal ions or their combination, thereby opening promising perspectives to get access to multi-catalytic homogeneous system adaptable to different types of transformations such as Lewis acid catalysis and phantom catalysis. By controlling the spatial distribution and local concentration of metal centers within the polymer architecture, these systems provide a good platform for fine-tuning catalytic behavior and enhancing overall performance. So thank you for attention. That's end.
Thank you very much for the interesting talk. And I will ask you about the oxidation state of copper cations in your structure. One of, and maybe the oxidation state influences the activity, compare copper and gold. Thank you.
You see, it's very bad connection. I don't hear you. Well, I don't understand.
The question was about the oxidation state of the copper in your compound. Is what one or two oxidation state of the copper?
Yes, it's two oxidation state of copper, of course. Unfortunately, I don't have the scheme of. Maybe if you want, I can I can ask by mail, and I can show you the scheme of.
Okay. The answer is clear. The oxidation state was 2. We have no time for more questions, so thanks you once again.